Okay guys, so let's go ahead and get started with these videos. So these videos are going to be lecture replacements for your Tuesday, Thursday classes. And my goal is to have these videos for you completed each weekend before we would have had our normal lectures in class, right? So, you know, the content that I would have covered in Tuesday, Thursday lectures going to be replaced by these videos, right? So I'm going to be aiming for the weekend before, but you can expect them no later to be posted on Blackboard no later than when your regular class would have met. Okay, so want to remind you or recommend that you continue doing what you've been doing before, which is, you know, read through the slides. You know, if they make sense, awesome. If not, then go back to the textbook in the appropriate section, get a little bit more depth from there to help aid in your understanding. Hand trace through all of the algorithms, make sure that you understand how they work, and then use these videos as needed, right? So the videos are going to be our lecture replacement, right? Okay, so what I wanted to do is I wanted to start off by just going back and briefly reviewing what we had covered before. Remember, I think it was what was it, Tuesday, we were talking about doing searches when some of your sensors weren't working, right? So, you know, we had gone through and we were saying, well, how can we do searching with no observation? You know, if we can't perceive anything, if our sensors aren't doing anything, right? So what can we do, right? Well, if that's the case, remember, you know, you can still accomplish a lot, right? We talked about coercing a state by taking a series of actions, okay? And we talked about defining, you know, what a belief state is, what functions we would need to help us with our searches, you know, talking about the physical state, the belief state, etc. What are the actions? We talked about, well, you know, if they're going to be safe, if they're going to be unsafe, you know, how's that going to be impacted? Talked about the goal test, path cost. We're just going to assume for right now it's going to be easier just to assume that everything is going to be the same cost. I went through this diagram here with you, talking about, oh, well, initially your initial state's going to be all possible belief states, right? And then through a series of actions, it's going to narrow down the possibilities, right? All right, so let's see, where were we? Okay, so searching with observations, we talked about that a little bit. You know, we talked about how we had to have this percept function that would allow us to figure out a percept for some given state S, right? And if it's a non-deterministic problem, well, then you'd have a set of percepts, right? Because you're not sure exactly where you're going to end up. You know, the fully observable problems, they're going to have the situation where the percept function is going to return S for all states, right? So if you perceive something about S, it's going to be S, right? And by BS, I mean S, you know, for some state. And, you know, the percept function for some state, if you're in a problem where you have no sensors or your sensors are broken, well, then that percept function returns null for any possible state because you can't perceive anything. Okay. Now, big thing with working with partial observations, many states could produce the same percept. We talked about this last time, and you know, we started talking about how transitions from different belief states, they're going to take place in 3 different steps, right? We have a prediction step, we have an observation prediction, and we have an update. Okay, so let me just remind you of these things. So the prediction state, for the senseless problems, this is going to be the exact same. What this just means is, look, I've got some existing belief state B, right? And if I can apply some action A to states, right, within that belief state, then I'm going to get a brand new predicted belief state called B hat, right? Now, there's going to be another step called the observation prediction, And so what that tells us is, look, these are all the sets of percepts, call that set O, that could be observed, right? So we have this possible percepts function. So B hat is your new state, and you're going to try to figure out, well, what are all the things that I possibly could perceive for all of the states in that belief state, right? So once you've figured out what all of those percepts could be, then it's time to update your belief state, right? So basically what you're doing is you're going through an existing belief state, that's B hat there, and then O is the set of all possible percepts in that belief state. You're applying all of them, and that's going to lead you to your new belief state. So you see B sub O there, that's your new belief state given a set of percepts O, right? And so then I gave you an example in class about how this works, right? So for a deterministic problem and a non-deterministic problem. So with the deterministic problem, we've got basically a one-to-one mapping again. We could start off in the top figure here labeled A. You know, we have a belief state with two physical states in it, state 1, state 3. Now if we go through here and we say, well, all right, well, what are the possible actions that I could take? Well, I could move right, okay? So if I move right, then I could end up with this middle belief state, and from there there's a set of percepts that I could have, right? The vacuum's in B, and it's either dirty or it's clean, right? So now if I update my belief state based off of those percepts, then that leads me to two new belief states, right? I have two single physical state belief states, two singletons, right? So a similar thing but different is going to happen in a non-deterministic problem, because remember, in a non-deterministic problem you're not exactly sure about what the outcome is going to be for taking your action. So in B here, in this example, what you have is the possibility for the vacuum either moving or not moving, right? So if we start off in this left belief state with physical states 1 and 3, and then we attempt to move right, or if we try to take the right action, then from state 1, one of two things is going to happen. Either the vacuum doesn't move, in which case the new belief state is going to have that physical state unchanged, or it will, and that'll lead to physical state 2, right? And then similarly for physical state 3, in that initial belief state, the vacuum either moves or it doesn't, okay? And so that gives us this intermediate state where then we have to go through and predict what the percepts are going to be, right? So let's go back and remind you what that function looks like. That's the possible percepts function. So we have the predict function, which leads to this middle belief state, and then we apply the possible percepts function, which tells us what all the possible percepts are. In this case, for example B here, you know, that the vacuum is in the B square and the square is dirty, or it stayed in the A square and the A square is dirty, or you know, we end up in the B square and it's clean, right? And so from there we do the update state, right? So that's driven off of the new belief state here and the possible percepts that we could perceive, right? So the result in example B are these four belief states on the, or excuse me, these three belief states on the far right, right? One contains just a single physical state. Two, the middle one here contains physical states 1 and 3, because that reflects the possibility that the vacuum cleaner never moved because it was slippery, right? And then we've got this bottom belief state that contains only the single physical state 4. Okay, so if you combine those three functions, right, then what we end up with is our result, right? So our results function is defined by all of those functions working together, and that's what this is showing us on the right here, right? There's the update step based off of the predict function, and then there's the possible percepts also playing into that because they define what O is. Okay, So the determinism again, where's that coming from? Well, in the case of the slippery world, the fact that the vacuum could or could not have moved, but also you're not sure what percepts you're going to get after you apply the action. Okay, so solving partially observable problems, right? We're going to use that result function that we just talked about, and once we have that, then we can apply the and/or search algorithm that we talked about before from, what was it, figure 4.11, right? So conditional plan is also needed too. We did talk about this a little bit last time also. Talked about how, if you have some initial percept, A dirty, what does that mean again? The vacuum cleaner's in square A and the space is dirty, so state 1 or state 3 covers that. And then if you do a suck action and then a right action, that could lead you to this belief state in the bottom right here. Okay, and if you are in physical state 6, well then go ahead and do some sucking action. Otherwise, you're clean, right? You're done. You've reached your goal state. Okay, so for creating an agent for partially observable environments, then this is going to be similar. The way you would code this thing, the way you would make this thing, the way you would build this thing, it's going to be just like earlier agents that were solving problems. You have to figure out what the problem is, and we've seen examples of that. You call a search algorithm, right? We studied multiple search algorithms in chapter 3, and then you do it. You do the solution, find out what that solution is, and you execute it. So there's some similarities there, but there are some differences, right? So what's the solution? Not a sequence. It's a conditional plan. Why? Because if there's non-determinism in it, you don't know where the agent is actually going to end up or what the outcome of an action is going to be. But also, if it's partially observable, you're not sure exactly which state you're in after the action's been taken anyway, because different states could be reporting the same percepts. Okay, so that agent is going to need to keep track of its belief state, and it's going to need to keep updating that belief state as it's doing actions and as it's experiencing its percepts or sensing its percepts, right? Depending on exactly how the environment's defined. So an agent that's working in a partially observable environment has some similarities to agents we've seen in the past, but some key differences. All right. So this thing's going to follow the earlier prediction, observation, update process that I just outlined or that I just reviewed with you, right? Except here's the difference, right? So the percept comes from the actual environment, right? Whereas in what we just reviewed, the percepts were the result of the agent's calculation or an agent calculation, right? Because it figured, well, what are all the possible percepts I could have? And then you based the update to your belief state off of that. Whereas here, the percept's going to come from the actual environment instead of that calculation. So we can have our update function call look a little bit different. So if we're going to have an existing belief state B and we think we're going to apply an action A to it, right, then our update's going to be based off of what we predict, right, the outcome of our predict function, but also the actual percept that we've perceived, right? So once we've actually moved in this partially observable environment, you can perceive where you're at in the environment after you've done your move, right? But the thing is that you might have multiple states you could be in, okay? Because of the fact that different states could give you the same percepts. If you can't observe the entire state, then you can't know for certain where you're at. So you have to combine this prediction step plus also the percept that you've sensed after you've made your movement. And again, that percept is coming from the actual physical environment. Okay, so here is another example that we looked at briefly, and the way this worked with this example is we changed the problem so that any one of the squares or any square can become dirty at any time unless the agent's already busy doing some sucking, right? So if you look at the far left belief state, we got those two physical states, state 1 and 3. Okay, so with state 1, we could either, we got the vacuum on the left hand side, and both squares are dirty. State 3, vacuum left hand side, square is dirty, but we're not exactly sure where we're at just yet. Okay, so let's say you apply the suck action, right? Well, suck action guaranteed, you're gonna, when you suck, you're getting that dirt up. Okay, so square can't get dirty on accident with that action. So that leads us to one of two possibilities in our updated belief state, right? So, or our predicted state, which is that either physical state 5 or physical state 7. Okay, now from there we can sense, right, what the actual environment is, right? So vacuum is an A and that square is clean. We can sense that, right? That's from the physical environment. It's not the result of calculation, right? So if we're in that, if that's the case, then we can update that belief state to say, okay, well, we're either in physical state 5 or we're in physical state 7. Now, if we move right, or if we were to try to apply the action move right to either of those states, then remember, we've got the possibility now of a square getting dirty or not. Okay, so if that's the case, we can transition from state 5 to state 2 or state 6, right? Because if the square we left becomes dirty, then we're back to we're at state 2, where the vacuum is in the right square and both squares are dirty. If not, state 6, which is the vacuum moved without any new dirt being applied, and a similar situation with state 7. Right now, with state 7, moving to the right, could possibly end up in either 2, 6, 4, or 8, because after the movement is finished, that floor space could get dirty, right? Or not, because again, moving right can cause a square to get dirty. But either way, once that right action's been taken, we can sense what the square is actually like, right? That's from the physical environment. So if we sense that the vacuum's in B and it's dirty, then that means that we're either going to be in state 2 or we're going to be in state 6, coming from 2 or 6. Okay. All right. So this is where we continue with the new stuff. I think I'm pretty sure that we left off here on Tuesday. So real world itself, think about that. It kind of makes sense that it's almost always a partially observable environment, right? You don't know everything there is to know about the real world all the time, right? And so almost always there's going to be some things that are hidden from you that you kind of have to, I don't want to say guess, but deduce, right? Now, in such an environment, or like in any environment, but in this environment, what we're talking about here, the intelligent agent, its belief state, it has to stay updated, right? So that's going to be a continual process, and this is what we've kind of outlined and given examples for so far, right? That belief state has to stay updated. So the process for this, the function for this, there's many names for it. Sometimes it's called monitoring, sometimes it's called filtering, sometimes it's it's called state estimation. Now, the previous equation, right, that's an example of a recursive version. So we have the predict function given some belief state B and an action A, right, and taking into consideration the actual physical percept that we experience from the environment. All of that together, it's kind of a recursive definition, right, or there's a recursive version for it. If you go back and look at all the definitions for the function, you can see it play out. But that's going to lead to our new belief state. Okay, so the new state is going to be a function of the old one, not the entire percept sequence. Now, it's really important that this process execute really, really quickly, right? Can't fall behind at all, because in the real world, if the agent is perceiving its environment, it's trying to make decisions, it has to have an idea of its, what could be possible. It has to know what it's thinking about the world as really, really, really quick. Right? Because if the real world changes too quickly, then the intelligent agent, that agent's going to have to start making guesses. What do I actually believe here, or what actually is the real world like? And you're not going to be able to go as algorithmically or as deliberately as we've talked about in the previous slides or previously. Right? You might not be able to absorb the information. If you can't absorb the information fast enough, then you got to kind of fill in the gaps as far as the agent is concerned. So this updating, this keeping the belief state up to date, very important, has to happen fast. Otherwise, you're making guesses on your own belief state. You're not even sure what you believe about reality at that point. Very bad. Okay, so what we discussed so far up to this point has focused on, having environments that were continuous, having environments that were continuously subject to change. To be more specific, stochastic environments, right, where there's some randomness that's going on in there. So now we want to look at an example of a discrete environment where we have, just something different to think about. In a discrete environment, we've got some deterministic sensors, so there's no random chance that the percepts are going to be wrong or anything like that. And we're going to have non-deterministic actions. So what does that mean? That means that environment, discrete, right? One action is going to lead to another, and deterministic sensors, we're going to sense what we're going to sense. There's no chance that we're not sensing what we think we're sensing. In non-deterministic actions, well, we might decide to take an action, but not know what the outcome of that action is going to be until we've taken it. Right? So it's not a guarantee that if I choose to move right, then I'm actually going to move right. Okay, so I'm going to explain this with an example here, and this is going to be an example of what's known as localization. Right? So being able to figure out what happened based off of what you sense about the environment, okay, and checking changes to that environment from where you were a second ago to where you are now. So anyway, the task is localization. So in this example, we have an agent that's broken. We got a robot that's broken, and it can't control its movements. All it knows is that it can move, okay, and the environment which the agent is acting in is going to be just a simple old maze. And the problem we have here is that this robot, it only moves in a random direction. Okay, and after taking that random move, has to figure out, well, where am I at within this maze, right? So it's going to be able to sense where it's at. Okay, so it's going to have 4 sensors. It'll be able to sense the north of it, the south of it, the west of it, the east of it. So 4 different directions. Okay, but the actuators, they're broke, they're messed up, they're jacked up. The movement's going to be random. Okay, so here's the scene. Okay, so in the top of the figure labeled A, the robot could be in one of 4 locations in this maze, right? So the first observation would be, or the first percept would be NSW, right? So E1 equals NSW. So what does that mean? What that means is that the robot has perceived that there is a wall to its north, to its south, and to its west. So if you look at each of these positions that are like a little mini bullseye, right, dark circle with the bigger circle around it, in the upper left-hand corner, that percept holds. So to the north of it, there's a wall. To the south of it, there's a wall. To the west of it, there's a wall. Now, if you look at the bullseye-looking icon to the right of it on the same row, well, to the north of it, there's a wall. To the south of it, there's a wall. And to the west of it, there's a wall. And then along the bottom row, similar kind of thing. Look to the north, south, west, there's walls there. Okay, now, if the robot takes a move action, okay, if the robot takes a move action, it's going to end up moving somewhere. It just doesn't know where, because remember, the actuators are broken. So You know, it might try to move left, it might try to move right, up, down, whatever. We don't know which direction it's going to move. Now, after it moves, remember, its sensors are good, so it can perceive north, south, east, west if there's walls there. That's fine. So if after it takes its move action, right, it senses north, south, okay, what are the possibilities? Where could it be, right? From one of these four starting points, possible starting points, its belief state, it believes it could be in one of those four places. After taking a move, it senses north, south, right? Well, let's take a look at the top row, left possibility, okay? If after it moves, it senses north, south, and that's it, then that means it might have moved one square to the right. That's the only possibility. And so that would lead us to B, right? Now, if the possible starting position to the right of that on the top row, after movement, you know, the only way it can move would be to the right also, because there's a wall to its left and south, but it wouldn't perceive south, it would only perceive north, so there's no way it could end up there. Okay, now let's look at the bottom left-hand corner. It takes a move. The only possible place it could move would be to the right if it moved at all. Its percept would have been south and east, right? So there's no way that it could have ended up there. And similarly, if the initial position to the right of that initial possibility after the movement order or action was taken, if it moved to the right, then its percept would have just been south, right? And so that wouldn't have matched up with what it actually did perceive, which was north-south after the move. So because of that, the only possible place it could have ended up was where it's located in the B portion of the figure. Okay, so what's the summary? What's the big idea here? The robot can tell where it moved, right? How? It just compares what it observed. Okay, it didn't choose the direction that it moved into, right? All it could do was move because its actuators were broken, but perceived where it was at before the move, took a new move, perceived where it was at that point, you know, after the move was taken, compare the two, and you can imply or infer or deduce or deduct or whatever you want to say, you can figure it out. Okay, so that new location in B, that's the only possible place that it could have ended up based off of those two percepts, right? If you say E sub 1, E sub 2, maybe call that event 1 and event sub 2, right? But anyway, so, you know, this is kind of what, you know, the second point, the second bullet point here, this for this update, predict, update function, this is kind of summarizing what just happened, right? Where we had some kind of move, right? We had our update step, right? We're updating or trying to update based off of our belief state given the north-southwest percept, right? And so now we're predicting where we could end up based off of a move, and then remember that update gives you a new belief state, and so we do another update, right? That's the second event essentially. So, and we're accepting that north-south percept. So basically what this is doing, all that to say, right, that the predict step, what is it doing? It's growing the belief state. It's making the major contribution here, okay? All right, so that's gonna bring, that gets section 4.4 done. So we've got one more section to get through here, and then this chapter is over. So section 4.5. Okay, so let's talk about online search agents. Let's talk about unknown environments. Let's talk a little bit about offline search agents, right? And we're not talking about the internet here. We're talking about characteristics of how the search is done or how the agents are doing their searches. So what's an offline search? Okay, offline search, this is what we've been doing so far. This is how our agents have been working so far. You got an algorithm, it's finding a solution, right? And then the agent executes that solution. Okay, so you find that solution before it's applied to the real world. Now, with an online search, with an algorithm that's this type, what's happening here is that you're interleaving or you're alternating between thinking and doing. So you have computation and you have action, right? And these things are alternating. So with the algorithms that we've studied so far, the agents we've studied so far, the search takes place until you find your solution, and then the agent would execute that solution. With online search algorithms, you do a little bit of searching, you do a little bit of thinking, and then you do a little bit of action, and then you do a little bit of thinking, and then you do a little bit of action, then you do a little bit of thinking, and then you do a little bit of action. Okay, so there's a mixture there. It's not just one after the other. Okay, so when would you use these? Well, if you have a dynamic environment where things are constantly changing, you can't wait too long, right? It's like, if I have to decide whether or not I'm going to move left or right, I better make that decision pretty fast when it comes time to get that self-driving car to move through that intersection, right? Can't take too long as it's maybe cruising through the intersection and somebody runs the light. You can't take too long to decide, oh, I should probably turn the car, right? So it's good for those kind of environments. Also good for non-deterministic environments. Why? Because when randomness rears its ugly head and something unexpected happens, an online search algorithm can deal with it quicker than an offline search algorithm can deal with it. Because offline search algorithm, remember, find my solution, execute the solution. As the solution's executing, something new happens. Your solution is no longer valid. It doesn't work for you anymore. Okay, so online search algorithms, great. They're able to respond better to what's actually happening in the real world instead of thinking about, well, what could, right? Want to be able to respond to something that's happening even as I'm in the middle of trying to execute my solution. Right now, these guys right here, they're required. You got an unknown environment, you got no choice. You're going to have to use an online algorithm, right? Because you can't plan ahead. If you don't know anything about the world around you, right? If the environment is completely and utterly unknown, how can you plan ahead? How can you do a search through all the possible states when you don't even know what all the possible states are, right? So in an unknown environment, the agent has got a different type of problem. They've got an exploration problem. So every single action that the agent is going to take is going to reveal something to them about the world. They're going to learn a little bit about the world. So a couple examples: robot, right? Trying to explore a dark room, trying to figure out where everything is in the room. Where are the walls? Where's the furniture in the room? That sort of thing. Textbook also mentions newborn baby, right? Trying to learn about the world. You're learning by exploring, figuring things out, putting stuff in your mouth, putting your hand on the hot stove, going, ow, that hurts, right? So this is an example of an online search process. Okay, so an online search problem, we're going to have a situation where a solution's going to require that the agent does something right now. Can't think all the way through, can't project, can't simulate the entire outcome, right? So that's what we're going to have to explore. So essentially, the agent's going to have to learn a little bit about its environment as it goes along, right? And it's going to need, if it gets stuck, to be able to backtrack, to be able to back up and try to do a plan B, right? If it comes to a fork in the road, decides to go left, it needs to be able to remember to be able to go back and go right if going left in the first place didn't work out. But before we get there, let's look at some problems, right? Some examples of deterministic and fully observable environments where there could be some problems, and this is going to help us to justify needing a new type of algorithm, right? The ability to back up. So if I've got an action function that's listing my possible actions, if I got a step cost function that's going to take me from a state given an action to a new state, and I got a goal test function that's going to tell me I'm in a particular state, and if my result function is telling me for a particular state, for a particular action, I'm going to get to a state S for my agent, then consider this particular problem here, right? So in this case, the agent might start in S, right? The agent might want to be getting to G, okay? And so the agent might know, well, if I move north, right, I'm going to move north if I choose to take that action, but I'm not going to know about what's to the north of me until I actually get there. Now I might know the cost, I might know that to make that move, I might know if I'm there and it's a goal state, it's my goal state. I might know that if I start off in square S that I can move to the right or to move up, but I'm not going to know what's actually in that square until I get there, right? So, think about this then. If we move north, then we could get potentially stuck, right? By that I mean, if we move north and we hit a wall, we can't continue going north. We can't continue moving to the right because we're blocked off, right? So we'll need the ability to backtrack back to square 1, and then continue from there, right? But we're not going to know that there's walls there until we actually occupy square 2, 1. Okay, so that's going to eliminate any of those offline algorithms that we had previously, because those offline algorithms, you knew for a fact what the environment was going to look like when you moved. Okay, so we can add a heuristic function called h of s that estimates how far from wherever the agent is to the goal state. So let's say that the agent is in square 2, 1. Then if we know that we are, say, 3 units away, 1, 2, 3, maybe we're using the Manhattan distance heuristic, right? The start is 1, 2, 3, 4 away from the goal. Okay, fine. That can help us to kind of evaluate our performance, maybe even guide us a little bit, but we can definitely use it to figure out how well the algorithm did, or how well the agent did, I should say, excuse me. So we can compare the cost of the agent actually getting there, right? So let's say that the agent moved up 1, then it had to backtrack 1, then it had to move over to the right, then it went up, then it went down, then it went right, then it went up, then it went up. That's going to be like, what? It cost us 6, 7, something like that. Which is going to be far less efficient than if it just went all the way to the right, all the way up, right? So a heuristic function can help us out. And so we can compare the cost of the agent actually getting there to the cost of the agent getting there in the shortest possible time or distance or cost, right? So that comparison is going to be the competitive ratio. You want that ratio as small as possible, right? So if 1, 2, 3, 4 is the cheapest cost to get from start to goal, then we want our agent to go 1, 2, 3, 4, and we want that ratio to be 1 to 1. Okay, now it's possible it could be infinite, right? What does that mean? Well, you could have some states if they're irreversible, or if you're in a dead end, well, then that ratio is going to get infinitely huge or infinitely small. So what do I mean by that? Well, consider figure 4.2, the A portion, right? These are 2 examples. If the agent starts off at S and moves to the node labeled A, it's got a choice to make. It can go left or it can go right. If it decides to go right and then takes another step, now suddenly it's in a dead end, right? It's in a dead end. It can't go back left. It can only move right, and it's just in an infinite loop here, right? And so that is an infinite cost away from getting to the goal. Can't back up. Okay, similar thing can happen in the diagram or the graph directly beneath it. Same thing, just putting the goal in a different place. Okay, so that definitely can impact the actual cost that you're going to have to pay to get to the goal. Now, in example B over here, you have an example of an adversarial problem. Agent has to try to get from S to G, and these column-looking bars here, this represents obstacles that an adversarial agent or an adversary or an opponent has placed in front of the agent. And so as the adversary is placing these obstacles, then the agent has to make a decision to go around the wall, for example. And so that's going to impact the overall cost of getting from the start to the goal. Okay, so for A, you're going to have a failure in one of those cases, right? So, there's a possibility of you failing on either one of these sides. You're never going to hit that goal state. Okay, so B, again, example of the adversary argument. Okay, it's trying to make the exploring agent travel further than it otherwise would. Now in real life, you can have some dead ends as well, where the agent could fail. So robot hits stairs, falls down the stairs, Roomba blows itself up, rolls off a cliff, blows itself up. Other types of terrain that are impassable. Okay, now the textbook, the examples there, they assume for the algorithms that the spaces are safely explorable. Your agent's not going to get to a place where it's going to not be able to recover from. Okay, it's not going to automatically destroy itself to be able to explain these concepts easier. Okay. So here's some more information about the online search agents, right? So what these guys are doing is that after they take an action, they're going to get a percept, right? And so that percept is going to tell them a little bit more about the world, right? So you can imagine, maybe one of your favorite 4X games, and there's the fog of war, right? And so an agent decides, well, it's going to move its scout north, right? And so that's going to uncover a little bit about the map, right? So the agent itself, its knowledge of the world, its belief state, its map gets updated a little bit, and that updated information helps to decide what the agent's going to do next. So how this plays out effectually is that you're expanding one node at a time, and then an action gets taken, right? So this is different than the offline algorithms, where you can expand all the nodes you want, you can do all these simulations, you can play out 10,000 virtual games before you decide a move, or you can plot out 20,000 different particular 20,000 different paths, and then make a decision maybe based off of the path cost or something, right? So does that, the algorithm just keeps right on going. You can forecast or see into the future all these potential different moves that you can make, all these actions you could take to come up with a solution that's going to get you there, maybe with the cheapest cost. With online search agents, that doesn't happen. One node gets expanded at a time, then an action is going to get taken, right? So this should say online algorithms, not offline, my apologies. Online algorithms, they use depth first search, and they're going to expand nodes in a local order, right? So you'll see how this plays out when we look at some of the algorithms. But so this is as opposed to going across an entire virtual tree doing the breadth first search. They're doing a depth first search. Okay. All right. Okay, so let's talk about an algorithm that can actually remember, can actually learn a little bit. And what this is an online depth first search agent. Okay, so you pass to this thing. Let me just give you the highlights of the algorithm again. I won't spend too much time on it. You're going to want to hand trace, hand trace, hand trace, hand trace, hand trace. Okay, but let me give you the highlights of it. What's your input? You've got some percept, S0, and that identifies your current state, right? Because the agent perceives something about its environment, right? Keep this in mind. It perceives something about its environment through its sensors, and then it has to take an action. So this agent function is taking something it perceives about its environment right freaking now, and then it's going to decide, I need to take an action. So here's the action that you're going to take. That action would then get fed over to the actuators, and the agent, or the agent, excuse me, would take its next move. Okay, so what's persistent here? What's global? What is going to maintain their state in between function calls, right? What are the static local variables? What are the global variables? Okay, so what you have is result, a table indexed by state and action, actions, things going to be initially empty. Untried, table that lists for each state the actions not yet tried. So for each state, the actions not yet tried. Unbacktracked, table that lists for each state the backtracks not yet tried. So what unbacktracked, what that table is keeping track of is, imagine if, you know, we're in this bottom graph and our agent is at node A, right? And it decides to go left, okay? Now, if it hits a dead end, the backtrack would be where agent A was, right? It'd want to be able to backtrack, move itself back to that state, to that place in the environment, in the physical environment, and then try the alternative route. Okay, so that's what that's what we're talking about when we talk about backtracks. So the unbacktracked table, that is listing all of the alternatives for a particular state, right? So for each state, the backtrack's not yet tried. S and A, the previous state in action, initially null, because that agent starts somewhere and it didn't do anything to get there. It's where it's starting off, right? Roomba is at its charger, and then you're about to hit the start button or the clean button, but you haven't done that yet. So its previous state in action, no, nothing there. Okay, so how does this algorithm start off? I'll just go through this briefly. Goal test. Okay, if the percept indicates the state that is the goal, done, stop, the agent stops acting. Okay, but if it's a new state and that state isn't in the untried table yet, then you add to the untried table, indexed by that percept, all the actions that could be taken by that state indicated by that percept. Okay, now if the previous state is not null, then what? You add to the result table, indexed by the previous state and the previous action, the current percept, right? The percept that we just passed to this function indicating a particular state. So what that's saying is that the outcome of the previous state and action is this new percept. Okay? Now, add the previous state to the front of the unbacktracked table indexed by this percept. So what this is saying is that the previous state, that's going to be our plan B. We can go back there and try again. Okay? Now, if untried, right, for this percept that we just passed is empty, then what does that mean? That means you've tried all of the actions for the state indicated by this percept. Okay, so there's nothing left to do for this particular state. We've tried everything. So now let's go and try to go back. Let's try to attempt to backtrack. Let's go to unbacktracked. Okay, for this state. Right? If that's empty, that means we've tried all of the alternatives. Okay, we've gotten here, we've gone through all of our actions, we can't advance any further, so now we want to back up. Well, if our backup possibilities are empty, we're stuck. There's nothing to do. We're not going to find our goal state. There is no path to get there. Otherwise, right, if unbacktracked is not empty, that means that we can go back. We can try an alternative. And so we'll go ahead and we'll pop that alternative for the state we just perceived. Okay? Now, the alternative is if untried for a particular state is not empty, then grab the next action. Right? Grab the next action, and that's what we're going to return. We're going to tell the agent, oh, try this one. You haven't tried this yet. Right? And so then the agent that, or the state that we just perceived becomes the previous state. Okay? So you got the video. You can rewind this as many times as you need for me to explain how this thing works. Hand trace it on your own, but here's a couple more points here, right? There's a table used to keep track of the map of the world, right? right? How's that built, or what's that table result? Okay, and that's recording the state resulting from action A in state S. Okay, I already explained that. You need to try any action that is yet to be tried in the current state. That's what untried was for, right? That's what untried was for. Okay. In this online search, if all of your actions are tried, you try to do your backtrack. That's what the unbacktrack table was for. Okay. To get back, table of previous states visited, that's kept, right? That's what unbacktracked is for. Okay. Now, if there's no more states for you to go back to, you're done. Again, hand trace, hand trace, hand trace, hand trace. You've got to put the time into these algorithms. Right? The algorithms themselves are simple if you just put the time into them. Right? It's a lot harder to explain them than it is to understand them. Okay, so the agent doing its backtracking according to this algorithm, you have to have state spaces that are reversible, that can be undone. In other words, you have to be able to go back in the first place. Okay, so worst cases, you know, I mean, and what I mean by that previous point is, I mean, imagine Roomba going and hitting a wall, right? It has to be able to, you know, undo that. It has to be able to turn around. That's all that means. Okay. Now, in worst cases, links are going to get traversed exactly twice, right? When you're just doing exploration, then this algorithm is going to be optimal, right? Because you're just going to be, if all you're trying to do is uncover unknown spaces or learn, well then the algorithm is just fine. Okay, now the competitive ratio can get really, 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 really bad if the goal is really close to the start state, because your agent might have gone off in the wrong direction and have to work its way back. Okay, so how can you increase the performance there? Iterative deepening. Right, some version of iterative deepening that we saw from chapter 3 would work. A uniform tree could also help, right? Or let me rephrase. Sorry. If you have a tree that's uniform, is what I'm trying to say. I was thinking about the uniform cost search. Sorry about that. Right? If the tree is uniform, I mean if it's pretty much a balanced shape, I guess you could say, right? Where you know, each direction has the same number of actions per se, and maybe they all lead to the same goal, then that ratio can be pretty small. Okay, so let's talk about an online local search or online local search. Now, the hill climbing search, it's local. It's a local search because it only cares about its neighbors, right? But it's an online search algorithm, right? It only keeps one node in memory. Remember we said previously that essentially with these online algorithms you're expanding a node and then taking actions, right? So hill climbing search is an example of this. Right? You know, as opposed to the offline search algorithms, which are expanding nodes all over the place, right? Creating this huge old tree. But anyway, so hill climbing search, online search, local search algorithm, problem, can get stuck. It's stuck at a maxima, right? So, you know, you could take, we looked at some different ways of getting around that. Random restarts, right? So for here, let's not do that. Let's not talk about random restarts. We talked about that before, right? So let's avoid teleportation magic. How about an alternative, right? Let's look at an alternative and talk about that for a minute or two. So an alternative would be to take a random walk, right? So what? At random, pick an action. And we talked a little bit about that in class, right? The possibility of that. Let's dig into it a little bit deeper, okay? So let's say that we have this type of environment as laid out in figure 4.2.2. The agent's starting at S, trying to get to goal state G. Okay, so it can move, you know, it can move to the right, 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 you know, just go all the way straight, moving right constantly till it gets to G. But if you're moving in random directions to try to avoid those maxima, then you might move right, and then you might move down, and then you might move back up to your start place, then you might move right, and then down, and then back up, and then down, and then back to your start space, and then to the right, and then back to your start space, and then to your right, and then to your right, then down, then up, then to your left, then down, then up, right? So eventually, roll enough dice enough times and you'll randomly stumble across your goal state, right? Which would have been that global maximum or that global minimum for hill climbing. Okay, so you will find it in a finite space. If the space is finite, you'll find what you're looking for. But as I was just explaining with the example I just gave you, you're really freaking slow, right? You're taking one step forward, two steps back. Maybe you get there eventually. Maybe it takes you an hour, maybe it takes you 10 years, whatever, right? It could take forever. So how can we improve that? Okay, replace the randomness. And I say, yeah, I mean, replace the randomness, right? Let's have some memory. Let's remember stuff. Okay, so here's what I mean, right? So you can take your best guess, right? Take your best guess right now of how to get to a goal from a particular state you've been to, right? So let's remember that. If I'm here, right? My best guess getting to the goal could be 5. Let's remember that, okay? And let's use that memory to help us make better decisions in the future about moving towards that goal, okay? So we'll start with some guess, right? So we've got some goal, some cost for a state to get to the goal, uppercase H for state S. We'll begin with the heuristic guess using a heuristic function, lowercase h. We'll update as we go. So the agent is going to make decisions on moving based off of those guesses, right? And the cost to move from one state to another, and the cost of those guesses for each one of those neighbor nodes. Okay, so what do I mean by that? It sounds a lot more complicated than it is. Let's look at figure 4.23. Okay, so let's say that A is a particular environment. Okay, it's the very first example up here. Now each one of the circles represents a node, a potential state, or a particular state. The arrows represent actions we can take. We can transition from the gray state labeled 2 to 9, or we could go from 2 to the white state 2, right? The cost to go to either, just the step cost, is 1, okay? But the numbers in the circles represent the best guess of the cost to get to the goal state, right? So if I start off in this top environment, the environment configured as it is for A, and my agent is at the state that's grayed out, okay? So the cost, the guess to get from that state to the goal is 2, right? Uppercase H, S, right? Now, I have a choice to make, right? Now, to move to the right, to the state to the right, or to the state to the left, the path cost is 1 in either case, right? Now, which one should I take if they're the same, if the path costs are the same? Well, look at what the heuristic guess is if I end up in the left state, it's 9. Look at the one if I move to the right, it's 2. So that algorithm then tells me I should move to the right, okay? So when I move to the right, I'm going to remember the cost, or I'm going to update, right? So 2 plus 1 is 3. To move to the right, right? I take my original guess, which was 2, plus I have to add 1 to it because that's an additional movement that I had to take. So that means then that my guess has been improved, or I'm going to have to improve my guess, the cost. On line B, it reflects that. So that 2 becomes a 3. And my agent is now in this gray state over here. Now, the agent has to make a decision again. Should it move left or should it move right? Now, path costs are the same, it's uniform, right? Going to the left, taking that action 1. Going to the right, taking that action 1. But if I move back to the left, right, that guess is only a cost of 3 away from the goal, whereas if I move to the right, it's 4. So 4 plus 1 would be 5, 3 plus 1 would be 4. That's going to tell my agent, move to the left. But also, update what that guess was, what that cost guess was for the state you were just at. That becomes 4. You're remembering that. Okay? So now when it comes decision time, again, should I move left or should I move right? Right? Well, if I move to the left, it'd be 1 plus 9, which is 10. If I move to the right, it'd be 1 plus 4, which is 5. So my agent's going to bounce back. Okay? But it's learning each time. You see how each state's cost to the goal is increasing? It's remembering that. And it's taking that into consideration for future decisions. Okay? Now, on line D here, right, that's reflecting my environment. So the agent is at the 4 node. Now that's the decision. Does it go left, paying the path cost of 1 plus the guess of 5, or does it move right, paying the path cost of 1 plus the guess of 4 to the goal? Well, it's going to make that choice to go to the right because 4 plus 1 is 5, whereas if it went left, it would be the cost to get to the goal, the guess cost to get to the goal of 5, plus the action cost of 1, so it moves to the right. Updating the guess for the cost to get to the goal for the previous node, or for the previous state, to 5, right? So every time you make an action, the cost or the guess to get to the goal from the node you just left goes up, and you remember that. Eventually, you're going to whipsaw back and forth, getting out of your stuck state through those repeated guesses, those heuristic functions and updates of your memory of the cost of where you've been. Okay? So that cost that's getting updated each time went from 2 to 3, and then 4, and then 5, right? So that cost is getting updated based off of the cost to get from your current state, given an action, to get to your new state, plus the guess of getting to the goal from the new state. Okay? So this algorithm that we just described is known as the learning real-time A-star algorithm, right? So this is probably, you know, well, I mean, the previous algorithm had a little bit of learning in it too, because you were remembering where you came from, so you could try plan B, you know, so you could backtrack. Well, now this is another type of learning where you're updating your estimated cost to get to a goal from a particular state. This video's gone on long enough. I know that I'm over an hour and 15 minutes here, which is what our normal lecture time would be. So I'm going to end it here. So this video at this point is going to be the replacement for the Tuesday lecture, right? So the next video that I post, I'll go ahead and post this one as soon as it's finished encoding, and then the next video I'll work on, probably have for you tomorrow night. That will replace Thursday's lecture, and that's going to finish up chapter 4, and then we're going to start chapter 5, which is game playing and adversarial search, right? And then once we get through chapter 5, the following lessons we'll start focusing on the Lisp programming language. You'll start having some minor PPs, some minor programming projects to help warm you up to Lisp, and your next major programming project will be to implement a game playing algorithm for a simple game of tic-tac-toe or Connect 4. Okay, so thanks for suffering through that. Hopefully it wasn't too painful. And remember, what you want to do is you want to skim through those slides, see if they make sense. If there's any depth lacking there, something you missed, go to the related section of the textbook, read more there, hand trace through the algorithms, right? I'm giving you a high-level description, and listening to me ramble on about them is only going to do so much for you. You really got to engage with the material, right? And then watch these videos as needed. These are lecture replacements, and as you know, I don't take attendance for lecture or anything like that. So, I mean, yeah, they're required insofar as lectures are required. So take that as you will. Okay? All right. Thanks for watching. We'll see you next time.